Very much. Now we will hear our next presentation by Edita Stonkute from the Vilnius University. She will tell what could be done by observing exoplanet hosting stars.
Good afternoon, everyone. I will start to share my presentation. So I hope you can see and hear.
Yes, yes.
Okay, so I will present what work we've been doing with Europlanet Telescope Network facility. And at the end of my presentation, and this work is done together with a group that I am part of, so with Gražina Tautvaišienė, Šarūnas Mikolaitis, Renata Minkevičiūtė, Ernas Drazdauskas, and PhD student Ashutosh Sharma. So this stars with planet field started 30 years ago with planets orbiting a neutron star and hot Jupiter around Sun-like star. And probably most of you remember those exciting discoveries. And after that, our understanding how planets forms radically changed, because we assumed that planets form as our example solar system. But with those discoveries, we needed to change our models and our understanding. And today we know that there are several thousand exoplanets discovered and confirmed, and there are many more waiting for confirmation. And we started from planet detection using advances in radial velocity transit, direct imaging, and microlensing surveys for exoplanet detection and characterization. And now we can do high precision atmospheric spectroscopy of exoplanets using space-based and ground-based observation. And combining this all information observed with theoretical models, we can learn more about how planets form, how they evolve, also learn about planet interior and atmospheric processes. But today I'm gonna focus on learning more about stars that host exoplanets. And as Carolina already showed, we have this nice chart of discovery per year using different methods. We see that mostly we began discover exoplanets with radial velocities, and then transits took over the most discovered exoplanets. And if we look at the period mass distribution, we could see three big lumps that we can call hot Jupiters, warm Jupiters, and super Earth. So with these discoveries, we could directly see that the confirmed exoplanets are different and very diverse comparing to solar system. And exoplanet research is experiencing really nice and revolutionary times, because we also have dedicated exoplanet missions that you can see going from ground-based observations to space-based observations, space-based facilities, as it's shown in this nice ESO picture. Started with Korot, Kepler, K2, and TESS, and the future ones, HEOPS, Plato, and Ariel missions. And there are missions also sensitive to exoplanets to characterize already exoplanets that have been discovered. And today I'm gonna focus on ground-based observation using facilities on ground. And the star-planet connection after the discoveries being analyzed by many actually authors, and in 2001 Santos showed that the metallicity of or iron over hydrogen of planets hosting giant planets, of stars hosting giant planets, are more metal rich comparing to comparison sample that at that time has no planet detected around those stars. What do I mean more metal rich? For those who don't know this nomenclature, we will take a sun as a reference and we will say that it's a 0, and everything that is more than 0 is more metal rich, and everything that is less than 0 is more metal poor, okay, during this talk. And also later on, Deborah Fisher and Valenti showed that this the higher the stellar metallicity is being indicative of higher probabilities of giant planet detection. So at that time, the samples, the stars hosted giant planets. And later on, scientists wanted to check, is this metallicity planet connection still holds for different type of planets? And Sousa in 2008, using 66 planet hosts, shows that Neptune-sized planets do not form preferentially around metal-rich stars as giant planets do, and they can form at any metallicity. And later on, this work, this finding was confirmed by work of Ghezi, that Neptunes can form at any metallicity that you can see here in red. And the more we know about the planet, about the star, the more we can say about the planets and how those planets form. And the next step for sure was to look at the smallest planets, the rocky worlds. So the work led by Lars Bohave in 2014 showed this nice figure where you see on the x-axis planet radius and on y-axis metallicity. They show that rocky planets can form also as mini Neptunes at any metallicity, but also what we can see in this nice figure, that giant and ice giants still preferentially will form at a higher metallicity than the rocky worlds. And the composition of the planetary disk is thought to be linked to composition of the hosts, where the higher overall metallicity provides the building blocks for planet formation. And this is like a planet formation scenario. It could be core accretion, where higher metallicities imply more planetary building blocks. And how about other elements that we can look in stars hosting planets? Do they show any signs of planets? By the work by Israelian in 2009 showed that the lithium abundance of solar type stars is expected to be decreasing progressively with age. And for solar type, for solar temperature stars and sun itself, we see the depletion, additional depletion of lithium. So they suggested that this could be a presence of exoplanet. And they claim that metallicity excess could be results from either the accretion of the planet or planetimals on the star or the protoplanetary molecular cloud, because this exoplanet might decrease amount of mixing and deepen the convection zone, such the lithium can be easily burned, and we see this depletion. But later works do not show this finding using other criteria to select solar type stars. Later in 2008 and 2012, there have been work showing that alpha elements, elements produced in supernova type 2s, such as titanium, calcium, magnesium, they are enhanced in stars that host exoplanets, comparing to thin disk stars. And terrestrial planets, because in blue you see Neptunians and super Earth, and in red you see Jovanian hosts. So if you can follow the black line, which is for exoplanet hosts, and the green line is for comparison samples. So we see some kind of enhancement of those alpha elements at lower metallicities. So there have been works also analyzing other chemical elements in star atmospheres. And there are very different results. Some of them are saying that that stars with and without planets have no important difference in element over iron ratio. For example, refractory elements in Delgado-Mena work in 2010 say that there is no difference. And for volatile elements, Suarez claimed there is no difference, but later work by Delgado-Mena showed that after all, when we have a bigger sample of stars, we see that the ones who are smaller, that the ones that host smaller exoplanets at lower metallicities are enhanced in carbon. And knowing this all information, knowing those all abundances that we are doing, it can help to constrain the models, because theoretical study shows that, for example, carbon over oxygen number ratio, as well as magnesium over silicon ratio are important in determining the meteorology of extrasolar planets, because CO ratio controls amount of carbates and silicates formed in planets, and magnesium over silicon can tell us about silicate meteorology. So there are references that those works analyze this influence. And also studies, theoretical studies shows that planet formation pathways depends on chemical composition of the host star. And this CO ratio also can tell about giant planet host, giant planet, if the water ice condensation is the main driver of the giant planet formation. And also this is why our work is important in combination to theoretical works, because we can give some clues to them. So using Europlanet Telescope Network facilities, there are several telescopes that one can do spectroscopy, and I highlighted them here. Just only I found that this telescope in 1.3 telescope in Slovakia are stopped for renovation, and since we know better the Moletai Astronomical Observatory, because we worked before. So we initiated high resolution spectroscopic follow-up of exoplanets host. So what we are doing, we are using high resolution spectrograph at Moletai Observatory. It's 1.65 meter telescope, and the spectrograph is in 3 resolution mode, 345 and 60,000. And the spectral range is from 400 to 900 nanometers. So what we did, we selected from test space mission the candidate list that host exoplanets, And we observed those stars that has a minimal, if any, chemical composition information from high-resolution spectroscopy. So we've been awarded by Telescope Network 7 nights with this spectrograph, and we are currently working on the data. So, but I would like to show you what kind of nice results we can get using still Moletai Observatory spectrograph. And I will talk about our work that we just recently been recently accepted in the journal. And this work is chemical composition of bright stars in the northern hemisphere. So in this work, we not only derive the main atmospheric parameters such as temperature, surface gravity, metallicity, and microturbulence for many stars in the sample, 740 FGK type stars, but we also analyze the possible star-planet connection. And in the blue, you see thin disk star, galactic thin disk star, and the red thick disk star, and high and low mass planet hosts are indicated in green and yellow. And we can see that on the y-axis, we have those alpha elements that are produced in type 2 supernovas. And we can see that for planet host, we have a higher alpha over H abundance ratio. But if we look at C and O elements, C and O and magnesium silicon, we see that planet hosts and comparison samples are not showing any difference, but slightly larger CO ratio could be seen in dwarf stars that has low mass planets. Low mass planets, as I said, is in yellow. And we also analyzed star-planet connection looking on x-axis now planet mass and various different parameters like period of the planet, stars, mean radial distance from the galactic centrum, height from the galactic plane, and metallicity or iron abundance, also carbon, oxygen, CO ratio, and magnesium silicon. What's interesting is that we find a negative slope of CO ratio with increasing planet mass, and we take into account only hosts that are dwarf because giants experience evolutionary effects with carbon and oxygen ratio. So we don't take purple stars into account while deriving this correlation. And we have some also negative slope of this planet mass and magnesium silicon correlation, which is also very interesting. The gray dots are comparison, also planet hosts taken into account from Michelina work, and our magnesium and silicon and Michelina's magnesium silicon correlations agree very well. And we also looked at the condensation temperature and abundances difference of planet host and comparison stars. And in green, you see the host that has low mass planets. The blue ones are stars that host high mass planets. And the red one is the star that hosts both low and high mass planets. And it was shown that Sun shows deficit of refractory elements with respect to solar analogs, and this could be related that these refractory elements are trapped in the terrestrial planets in solar system. So refractory elements are the ones that has lower element condensation temperature. And what we can see from our results that all low mass planet hosts in our sample shows positive correlation regards condensation temperature, while the high mass planet hosts have diversity of correlations. And we see that the star that hosts both kind of planets have the strongest correlation, the steepest correlation. And I would like to finish my talk saying that we also looked possible factors that could be responsible for this trend. And we looked at the metallicity, if there is any correlation with metallicity, staral age, effective temperature, and metallicities. And we see some slopes here as well. What I wanted to point here is in my talk that chemical composition results that we are presenting will give information to exoplanet modeling, some priors to exoplanet modeling in theoretical work. So thank you for your attention.
Thank you, Edita, for your presentation. So now it's time for questions. So one question came to the Discord. Andrei Kovacs is asking, do the Europlanet Telescope Network telescopes are suitable for the follow-up observations and determinations of stellar parameters, chemical composition, or also can be used for the radial velocity observations in support to SG4, Gaia SG4, deriving planetary orbits and masses. So what about radial velocities? Actually, I don't know. Probably we could pass this question to contact people from the observatories. It is not clear what is precision of what is necessary precision of determining the radial velocities. So you should write what precision is necessary, and then the answer could come.
Yeah, I would suggest to contact Ukrainian team because they have 2-meter telescope with spectrograph. So maybe a new collaboration could start.
Yes, and also we can try at the Moletai Observatory.
Yes, yes.
Other questions? One last question. So,
may I ask a question?
Yes, sorry. One question.
Yeah, I have.
Zelensky.
Yes. Hi, very nice talk. Hello. I have short question and rather technical one. What is the method of determining the elemental abundance? I mean, do you use equivalent widths, or do you synthesize the spectra and make the fits to the observed spectrum and the line profile?
So for that work, we use the synthesis method for CNO.
Mm-hmm. Okay. Do you have your own pipeline, or you use some known radiative transfer code?
Yeah. We use I think it's turbo spectrum that we use for CNO.
Yes, from the Uppsala Astronomical Observatory.
Mm-hmm. Okay, I know that. Okay, thank you.
Yeah,
so